Hello, everyone, and welcome to the webinar. Our topic today is wearable AI in clinical decisions. It's great to see so many of you joining. This webinar is co-hosted by the Stanford Wearable Electronics Initiative and the Center for Artificial Intelligence in Medicine and Imaging. And I'm Angela McIntyre, the Executive Director of eWear. Katrina Dillard is eWear's Program Manager, and she's hosting this seminar on Zoom. Professor Zhenan Bao founded eWear to foster collaboration that enables breakthrough innovation for future wearable devices and their data. eWear has participation from more than 80 research groups across the School of Medicine and the School of Engineering, and we're very thankful for the support of generous donors who make these webinars possible. We encourage you to ask our speakers questions after each talk. Please type your questions into the Q&A window on Zoom during the presentations. I'm very pleased to be joined by Johanna Kim, who is the Executive Director of the AIMI Center at Stanford. Johanna, would you like to say a few words about the AIMI Center and then introduce our first speakers?
Yes, thanks so much, Angela. Hello and good morning. The AIMI Center is delighted to be here to co-host this webinar together with eWear. Our mission is to responsibly innovate and implement advanced AI methods and applications to enhance health for all. AIMI is led by Drs. Kurt Langlotz and Nigam Shah, and together with over 250 Stanford faculty, we are dedicated to democratizing AI by making data, knowledge, and transformative tools widely accessible, and also by fostering collaboration across disciplines and sectors. Today, as I mentioned, we're delighted to be co-hosting this webinar, and our first talk today on scalable approach to consumer wearable post-market surveillance will be given by Ben Viggiano and Dr. Krishna Pundi. Ben Viggiano is a second-year PhD student at Stanford studying biomedical informatics and computer science. He's advised by Ewan Ashley and Chris Ray. He is primarily interested in developing methods to utilize foundation models to advance research methodology in biology, medicine, and healthcare. And Dr. Krishna Pundi is a clinical cardiac electrophysiologist and instructor at the Palo Alto VA Medical Center and Stanford University. His research interest is in combining traditional epidemiologic approaches of understanding disease with novel methods of data acquisition to define clinical, demographic, and arrhythmia morphology features that predict cardiovascular events and death. So we're pleased to have this first talk, and Ben and Krishna, please take it away.
Well, thank you so much. Those are very kind introductions, and certainly I hope this is a useful topic for everyone. So I think, so Ben, you've got control if you want to click us forward 2 slides sequentially. Those are our disclosures. Now, I'm an electrophysiologist, but this is not an AFib talk. But that being said, it's a very useful way for us to be able to frame this issue. So just briefly, atrial fibrillation is a very common sustained arrhythmia. Lifetime risk is up to 1 in 4. It increases risk of major cardiovascular outcomes, stroke, dementia, infarction, heart failure, and it reduces quality of life. For some people, it can be asymptomatic, and so it has a range of presentations. But the reason it's such a big focus, and on top of the fact that it's a highly prevalent and incident condition, is that it makes it a natural, the fact that it's irregular, the actual rhythm itself makes it a natural target for photoplethysmography, PPG. And it was really one of these early conditions that we started addressing with wearables. If you go to the next slide, please. And then really, this is actually the right audience for this because some of the early work on PPG-based AFib detection was done not by industry, but in academic centers. And so this is just one example of a deep neural network that was applied to PPG data, pulled from a smartwatch. And then, so when folks came in for an electrical cardioversion to reset them for their AFib, they actually had they got strips, and then they created this algorithm to determine whether they were an AFib, and it was highly sensitive and specific. And there was actually an early indication of what happens with these models too, because when you took it then and applied it to an ambulatory cohort, you're not talking about a highly enriched population, then you had much worse overall performance. Now, next slide, please. Now, we know since then that there have been very large-scale studies, one of which was based out of Stanford too, on how we use wearables to identify atrial fibrillation. Specifically, I just want to briefly talk about how it works with one approach to how these models work is that so for the Apple Watch, there's an algorithm for notification. It collects a 1 minute tachogram every 2 hours to look at the overall waveform and looking for irregularity. If it finds an irregular waveform, then it increases the sampling frequency to every 15 minutes, assuming that the user is still. So it's not going to take any actual measurements if you're moving around. And then if it catches 5 out of 6 consecutive tachograms in a 48-hour period that are irregular, then that surfaces a notification saying that this person might have an irregular pulse. If it doesn't, then it reverts back to every 2 hours. And so there are various versions of proprietary algorithms that have done this. If you could click one more time there, Ben. And each of these studies have gone on to validate their own versions in terms of these surfaced notifications and downstream subsequent confirmation with ECG-based devices. If you go to the next slide, please. But this is kind of where the distinction between the consumer-grade technologies and medical devices becomes important. Now, medical-grade devices are the way the FDA thinks of them are instruments or machines, and there's a whole different set of words they use for them, but they are specifically used to diagnose a disease, cure, mitigate, treat, prevent, or prevent disease in man or other animals. And when something is a medical device, so I'm talking about things like a pacemaker or a hip replacement, these things have these prospective studies on safety and effectiveness, and there's large-scale device registries that track their performance over time. That's not true for wearable technologies. And so in wearable technologies, anything that falls into the wellness realm that just allows you to live a healthy life, the FDA doesn't specifically try to regulate those things. But you do have to, if you have a software that you want to send through that you then can surface certain notifications or send advice to your users, then those things need pre-market clearance from the FDA. And so that's where most of these go through, is that the actual specific software functions are cleared by the FDA, and then you're able to actually use them in the device. But they make it clear, these aren't actually diagnoses. It's just an opportunistic way to surface a notification. Go to the next slide. Now, just moving away from the regulatory side of things, how that matters for us as scientists and researchers is that when we do science on anybody who gets any sort of device, there's a there's a very stereotyped path to how we can do that research. Because there's a clinician seeing a patient or individual, they get a prescription, there's a device. And so between the electronic health record, codes like CPT and ICDs and device registries, there are ways to follow performance and healthcare utilization and long-term issues. Now, you go to the next slide, please. If we're talking about a wearable, that doesn't necessarily, work in the same way. And that's because first, you don't even have to have an entry point through a clinician. You can have a consumer that just picks up technology and then activates the device software function. And there's no registry. They might not ever end up in the health record. They may or may not have long-term medical follow-up. And these things don't come with any specific codes to show that this is part of care. So one more click for me, Ben. And so this really highlights why we need a way to efficiently identify these individuals with wearable notifications, because they are not typical patients. They don't come in with the typical disease or procedure codes, and we don't really know what happens to them afterwards. And so I'll pass it to Ben here to talk about what we did.
Thank you. Yeah. So our main idea was basically to use clinical notes as the method of finding these instances of patients who came to the healthcare system because a watch identified that they had AFib. And preparing for this presentation was really fun because it highlighted to me just how much has changed in the world of natural language processing since just 3 years ago when we were working on this. So what I thought I would do is I would try to describe like the state of the art at the time that we did this project, and then also kind of get into like what a similar project may look like today in the age of LLMs. So we conducted this project during a transition period in methodology in the AI space. Traditionally, machine learning approaches generally involve training AI for a single, very well-defined task, but the downsides of this approach is that generally these models require huge amounts of training data, and they're very brittle and they don't generalize well outside the examples that they're trained on. Today, these approaches are generally referred to as like narrow AI systems. And the transition I mentioned at the time was this shift to this new paradigm of AI with the rise of foundation models. The idea was that rather than training a system directly on a target task, we would instead train these very large models using simple tasks on huge amounts of unlabeled data. These tasks are generally self-supervised objectives, such as masked language modeling, where you try to predict a masked word given unmasked words in a sequence, or famously like next token prediction, which is what ChatGPT, the models behind ChatGPT use. These tasks allow these models to get really good representations of an underlying data modality that then can be repurposed for downstream tasks such as classification, enabling high performance. So at the time, the main models that were showing such promise were transformer based. And at the heart of transformers is the attention mechanism, which essentially models all pairwise interactions between different words in a sequence. The issue with this, when we were doing this project at the time, is that this attention calculation can be kind of computationally expensive. By default, if you have a sequence of n words, n squared attention scores are computed. So we used a variant of a model with a variant of attention at the time called sparse attention, which essentially only models certain, like a subset of these interactions to enable a little bit more efficient modeling. The specific model we used at the time was called Clinical Longformer. It had just came out with, and it was a big deal because it was a model that was further trained on clinical notes and had a max sequence length of 4,096 tokens. Just to like put this in comparison, this model had like 120 million parameters, which was like rough, like, a little bit larger at the time. In comparison to the models that we have today, such as like GPT-4, this is multiple orders of magnitude smaller. GPT-4 is estimated to be trained at like 1.76 trillion parameters. So now that we have kind of this pre-trained base model, the next part of this task is to train this classification objective. And the issue here is that generally your performance increases when you have more labeled examples. And in medical applications, this labeling is the bottleneck because this costs a lot of Krishna's time to spend going through, because he's often the best, doctors are often the ones that are best suited to determine which examples are positive and negative. At the time, I was working as a master's student in Nigam's lab, and his group had recently turned to this new method called weak supervision to do this like large scale labeling of notes using expertise that was distilled into these labeling functions to basically boost the performance. So I'll kind of get into a little bit of how that works here. So basically, weak supervision starts off with a manual annotation of a subset of relevant documents. In our case, we selected documents that had a mention of some wearable device. So like an Apple Watch or a Fitbit that had the capacity to make one of these like atrial fibrillation notifications. The next step is that we take these ground truth labels and we split this into like a development set that we are allowed to look at, and then a test set that we hold off for using until the end to assess the final performance of the final classifier. And we go through and we probably spend a few months just creating these, what are basically called like label functions. These are simple programmatic rules that can be applied quickly to these notes to try to indicate what we think this note would likely have. So for example, like a note that contained an Apple Watch and the word alert or another synonym, that likely was going to be something that would indicate that this note contained one of these instances that we wanted to catch. One of the things that Krishna found that when we were like reviewing them was that if a note contained the word buy or purchase, it often was not an example because a lot of times people would be talking about like prospectively, buying an Apple Watch to monitor AFib. So that was another type of note that came up a lot. And basically, once we have these notes, we train what's called a labeling model that kind of learns, uh, which combinations of votes from these different labeling functions are able to make these correct class predictions. And this labeling model is applied to a larger unlabeled subset of the relevant documents to basically create like a set of probabilistic labels. This then goes in and feeds into the actual training process for the model, and it's been shown in a lot of research surrounding weeks of revision that this allows you to get much better performance on the classification task. So we applied this methodology, plugging in weeks of revision to generate this probabilistically labeled training set. And we were able to get a very good classifier on these clinical notes that achieved like an F1 score of 0.83. This is a PRC curve, precision recall curve, just showing like the difference of sizes of documents, like these like training sets essentially that we use, showing that like the number of documents that we included in this probabilistic labeling led to better performance of the final classifier. If you want to know more about weeks of revision, I would highly recommend checking out Snorkel. This is actually a company that came out of the Hazy Research Group here at Stanford. And also the Shaw Lab has a great resource for kind of getting started with these types of like named entity recognition type tasks in NLP. So those are two resources you can look further at. Another cool thing that we decided to look at the time was that there was this very interesting model that came out from OpenAI called ChatGPT during the time that we were doing this project. And so we thought, why don't we just try prompting an open source version, much smaller open source version of these systems with like these notes and essentially a very simple prompt. And I remember our collaborator, Richard, was the one who did this analysis, and he messaged me on Slack, and he was like, "Oh my gosh, you will not believe like these labeling functions from these prompt-based systems are totally outperforming everything we did." So it's kind of cool as like kind of a callback to seeing the larger world of prompting LLMs kind of coming into focus at the time of this project. And then finally, I just wanted to quickly relate to like how this would be done today. Um, a lot of the training, the weeks of revision, the workflows that we were talking through previously probably would not be used. Like now, the models that we have available to us, both closed systems and open source systems, are so powerful that we could probably do this entire project just with some creative prompting. So just really amazing how much the methods have changed just in this like 3-year period. And I'll give it back to Krishna here.
Right, and we can maybe we can try to be a little bit more expeditious about the first couple slides here. So basically, from an outcomes research perspective, once you've established your index time point, which we used as the time and date of the notification itself, then we can sort of look at the relevant clinical outcomes around it. And so for as using that as time zero for both for all the individuals that we applied this to, then we could look back at their baseline clinical comorbidities, then their medications and so forth. And then from there, we look at sort of fixed time periods after the notification to get a sense of what we think is potentially attributable healthcare use related to that notification. And so we looked at immediate, like direct healthcare use, as in ER visits or an emergency or urgent care within 5 days. And then within the first 90 days, healthcare utilization in the form of things like ECG monitoring, echocardiogram, other diagnostic testing. Uh, keep going. As Ben mentioned, so once the actual the algorithm had been created, we then also applied it to our cohort through the Veterans Health Administration, which has a large text integration utility database. So basically, every note that's ever written in the Veterans Health Administration is in one massive database. And as you can imagine, there's other additional layers of computational issues and resources that come into play. And so, we don't have Tanya here who did a lot of this work, but there's a lot of sequential removal of um, you know, unnecessary types of notes that have, mentions to device type terms that are not really related to wearables or notifications. And so ultimately, what we were able to do is create this analysis cohort between the Stanford and the Veterans databases of nearly 15,000 patients with a predicted notification. Just briefly looking at the demographics, there were as you can expect, there's going to be a different patient population between Stanford and the VA. I think things to point out here is that the VA cohort generally tends to be a little bit sicker, a little more diabetes, hypertension, kidney disease. Stanford did have more AFib and heart failure history, which sort of speaks to the fact that we as an institution have a lot of focus on cardiology care and oncology care. And so that you can see as well, and slight differences in overall demographics. So, I use this as a way to illustrate the sort of effects of these notifications. And so, among all of the folks who actually got a notification or a predicted notification, about 9,200 of them had no history of AFib, and then about 6,700 of them had a history of AFib. For the vast majority, or for the majority of the folks who did not have a history of AFib, they did not then have an ICD code diagnosis of AFib within the first 180 days. And so that is a way that we've used in sort of other studies to get a sense of yield of these types of for different kinds of notifications. And so if you use that as a calculation, then the yield in non-AFib patients was about 14% in Stanford patients and about 25% in the Veterans Health Administration. So without a history of AFib, not quite. There are plenty of other things that cause irregular notifications or fast heart rate notifications. Now, compare that to those who actually have a history of AFib. The yield is really high, 87 to 90%, which is it's an interesting comparison to the actual initial clearance for these algorithms because they were done in non-AFib patients. Now, since then, there's been expansion. There's an AFib history feature for the Apple Watch. There's other wearables that look at things beyond just initial diagnosis. But certainly understanding that what they're bringing in certainly is going to affect the likelihood that you have a true diagnosis, and the need for verification as well. If you go to the next slide, please. And then within these populations, you can look at the use of different healthcare modalities. So things like an ambulatory ECG monitor, stress testing, echo, and coronary angiogram. And realistically, you want to look at things that are pretty commonly, or that are done at decent volume for either population, because you have to accept the fact that this is not a perfect cohort. And so you can't really hang your hat on small differences. But things that we could tell that sort of started bearing out is that for folks who didn't have a history of AFib were more likely to get an ECG monitor. That makes sense because someone wants to actually confirm the overall burden and their downstream AFib, and slight differences in overall echo use. We'll go to one last kind of clinical finding and then kind of turn it to the discussions. I think one of the biggest findings that we had from this work is the predictors of healthcare utilization for individuals getting a wearable notification. And that's because when we created a model looking at what predicted someone actually going to the emergency room or getting admitted to the hospital, and then subsequently whether or not they actually got testing in terms of ECG monitoring, stress testing, angiogram, or an echo. The fact that someone went into the ER and went into the hospital was a much stronger predictor of subsequent care than their initial baseline comorbidities, their CHA2DS2-VASc score, which is a way to evaluate overall your stroke risk in AFib, which tells you that this is an important target for quality improvement and sort of value-based care and health, because the choice that someone made to show up in urgent care or in the ER, that itself initiates a cascade of care that doesn't necessarily have, we haven't shown that that's making them any better. And so having care pathways might be a way to be able to reduce healthcare use in these patients, especially when it's not tied to their actual morbidity or overall risk. So just to briefly talk about our overall kind of thoughts here, if you go to the next slide, Ben. So overall, our work here, and again, knowing that things have changed since then, that you can do large scale labeling as a way to do post-market evaluation of wearable technologies. And this is true even more so today than it was when we started this project. And it's that much more important as well. We've seen so much more democratization of healthcare technology and information. And while we do all this, it's important to think about it in the context of how your yield, your positive predictive value of this notification or any other notification is going to be significantly affected by baseline disease states. And that's important both for how you do the research itself and then how you think about taking care of patients or approaching technology or healthcare-based interventions. And as we mentioned, the thing we found is that showing up in the ER or getting admitted was the most important predictor of healthcare use. And this is important overall for how we use devices as well, because if we can't set up good pathways for an individual or a patient to reach their healthcare provider, have their information interpreted and then responded to, then it may actually start driving up costs by sending people through inefficient care pathways. Then we have one more slide to talk about, and that's our limitations, right? And briefly, we know there's no negative controls here, so we don't have a record of everyone calling in with normal rhythm evaluations. So we're not calculating the true sensitivity and specificity of these notifications. And this is everything. We're not talking about just Apple Watch or just Fitbit. This is everyone who has anything that can create this sort of notification. And then we're still only getting the people who are coming into a healthcare system, an electronic health record. So that still leaves out large swaths of the population who aren't even making it to that point. So that being said, I would like to thank all the folks who worked on this with us. Natasha and June on the VA side who helped with that analysis. Richard was fundamental in how we did a lot of our coding and work. And then Nigam, not mentioned here, is Mintu as well, who were part of the the overall grant process and then the earlier versions of the CDH. So thank you all. And we'll take some questions. And I haven't looked at the Q&A for a few minutes.
Okay, great. Wow, what a wonderful talk. Thank you. So enlightening. And I think we have time for one question, perhaps. So let's see. This question is for Ben. First of all, you get lots of people saying, oh, nice talk. Thank you. But Ben, there's a question about how to cope with the problem of narrow AI and using pre-trained models. Did you use the concept of transfer learning for building a classifier, or maybe you can explain more about narrow AI?
Yeah, that's exactly right. So transfer learning was this kind of previous paradigm of using models that were trained for other tasks on a new task. That was where the paradigm of foundation models kind of came from. The thing that was a little bit different about the idea of a foundation model is that these were much larger. So organizations, institutions would put a lot of resources into training these larger models with the explicit purpose of having them, available for a wide range of downstream tasks. That was kind of like the difference between like transfer learning and like the foundation model paradigm. But essentially, yeah, essentially the same type of idea.
Great, thank you. And I do see there are more questions that have come in. And unfortunately, to keep us on time, we're going to go and maybe send some of these questions to you, Ben and Krishna, offline. So you could choose which ones you feel you can answer later.
Sounds great.
Sound good? Okay. Thank you
Great.
so
Thanks so
much.
much.
And I'd like to now go to our second talk. And the title of this talk is Exploring the Potential of Wearable AI in Clinical Care. And our speakers will be Arjun Mahajan and Dylan Powell, who are both members of the editorial team for Nature Digital Medicine and News and Views. Arjun Mahajan is a student at Harvard Medical School with a focus on clinical informatics and autoimmune diseases. His work centers on applying machine learning and multimodal large language models to improve diagnosis, clinical decision-making, and patient safety. Previously, Arjun conducted research at Kaiser Permanente and helped people develop wearable technologies to address impairing motor stereotypy. He completed his undergraduate degree at UC Berkeley and then earned a master's degree in data science. And we also have presenting Dr. Dylan Powell, who is an assistant professor in public health and innovation at the University of Stirling in Scotland. Prior to joining the university, Dylan worked for the Deloitte Healthcare and Life Sciences practice and was the knowledge sharing lead for the UK Deloitte Clinical Network. Dylan's professional background as a clinician and researcher has spanned the National Health Service, academia, professional sports, and industry. His PhD research in computer science explored the use of wearables and digital biomarkers in neurological conditions, including sports-related concussions. Welcome, Arjun and Dylan.
Thanks so much for that kind introduction, and thank you to Stanford, eWear, and AIMI for having us today. So we were asked to base today's talk on our recent editorial overviewing the current landscape and future directions of AI-enabled wearable technologies in clinical care. And so we'll begin by exploring current gaps in clinical care that motivate the need for data-driven decision-making and wearable technology. We'll then talk a bit about how wearable AI systems are being developed to address these gaps across different domains of care and recent advancements that have positioned modern wearables to be more successful than their more traditional counterparts. And finally, we'll discuss important considerations for their successful development, deployment, and real-world integration. So according to the CDC, around 6 in 10 adults have at least one chronic condition, and around 5% of the adult population have complex medical needs defined as 3 or more chronic conditions plus functional limitations. In parallel with this trend, the share of US adults taking over 5 prescription drugs rose from about 8% in 1999 to almost 20% in 2018. And as patients increasingly live with multiple conditions, often chronic conditions like diabetes, heart failure, and depression, managing each condition separately becomes increasingly challenging. And to meet this challenge, wearable AI potentially enables the ability to monitor multiple physiologic systems simultaneously. For example, in tracking parameters like heart rate, glucose, and mobility, allowing for unified oversight and earlier recognition of compounded risks. Another important part of the increasing complexity of medical comorbidities is that patients frequently transition between specialists, hospitals, and outpatient care, often with gaps in communication. Wearable devices can potentially provide a longitudinal data stream that stays with the patient, helping create a common objective data set to support coordinated, informed transitions. Another key challenge that healthcare faces is increasing service utilization, a trend prevalent across many countries. In the US, annual emergency department volume rose almost 20% over this past decade. And in the UK, just this past May, the waiting list for elective care stood at around 7.4 million cases, with around 3 million patients waiting over 18 weeks for elective care. This increased demand is also partly driving a shift towards home-based health services as health systems struggle to fully meet care needs. And in addition to the increased demand, health systems are facing significant workforce shortages. In the US alone, the Association of American Medical Colleges projects a shortfall of up to 86,000 physicians by 2036 as retirements outpace new entrants, which is at least in part driven by burnout and attrition in addition to training bottlenecks. And globally, the WHO forecasts a deficit of around 4 million nurses by 2030, compounding bedside staffing gaps and escalating burnout. So overall, against the backdrops of increasing demand and decreasing provider availability, wearable AI becomes an increasingly pragmatic and even necessary response. Through providing a relatively continuous stream of health data, wearables can often act as extensions of clinical oversight, flagging emerging issues, sustaining engagement between encounters, and helping focus human capital where it matters most. And a final challenge that bears mentioning is that contemporary healthcare often operates in a somewhat reactive paradigm where intervention often occurs only after patients are symptomatic or have established disease. The system relies heavily on patients to recognize their symptoms or complications, access care reliably, and then requires providers to piece together often episodic data points to reach an accurate diagnosis or treatment decision. This approach inherently builds delays into the clinical care process, often missing critical windows for early intervention when treatments are most effective and less costly. Research suggests that diagnostic delays occur in up to 10 to 20% of patient-clinician encounters in the US and contributes to significant morbidity, while research in the UK similarly suggests that 1 in 4 patients with conditions like cancer experienced a delay to their diagnosis that could have been avoided. Wearable AI technologies potentially offer the ability to help shift this paradigm from reactive to proactive care by tracking baseline trends and identifying subtle deviations over time. These systems may flag early signs of disease and enable more effective and earlier intervention. So to take a step back and provide some definitions, wearable technology is a very broad term that essentially refers to any technology that is designed to be used while worn. And for the purposes of our talk, we'll use the term AI-enabled wearables to refer to wearable devices that use machine learning or other AI algorithms to collect, analyze, and transmit health data in real time. These systems represent an advancement from traditional wearables, which have typically relied on more rigid threshold-based monitoring systems and required greater human supervision in both development and data interpretation. In the past couple of years, these devices have become more robust in their ability to detect patterns across multiple sensors, adapt to a user's individual baseline, and operate with relatively minimal or less human oversight, allowing for the generation of more actionable clinical insights than previously possible. And to provide some context over the next couple slides that likely many of you are already familiar with, here is an abbreviated overview of how many modern AI-enabled wearable devices process data and how their capabilities have evolved from more traditional rule-based systems. In traditional wearable systems, signals like voltage or current are typically captured by sensors and sent into data pipelines to be transformed into more interpretable values, factors like heart rate, pH, or metabolite concentration. And this transformation in the past often has relied on predefined conversion functions using techniques like regression analysis, which have often relied on human supervision and or potentially static assumptions about signal characteristics and data relationships. More recent devices have changed this approach by substituting human supervision with machine learning algorithms, making this entire process more end-to-end learnable. This means that systems can now learn directly from raw sensor inputs to final outputs without requiring human intervention at each conversion step. For example, once secondary data are extracted, the pre-processing steps, often referred to as feature engineering, can now also often be automated. This includes outlier and anomaly detection, handling of missing features, noise reduction, dimensionality reduction, and data normalization. Once the features are prepared, they are passed into models built to perform functions like classification, regression, or clustering, depending on the goal. These models may be trained using labeled data, for example, where a known health state is assigned by clinicians, or may use unlabeled data to detect clusters or patterns on their own. Those are just a couple different forms of labeling. As was just highlighted in the past talk, there are also weakly supervised versions of learning and other forms as well. The model design also depends heavily on the amount and quality of the available data. In settings with limited and individual specific training data, such as single patient EEG recordings for seizure detection, models such as support vector machines or random forests can sometimes outperform deep neural networks, which can risk overfitting. But in more common conditions with larger data sets, such as in arrhythmia detection, more complex models may be able to be trained quite effectively. These systems can also extract highly nonlinear patterns between obtained signals and desired outputs with relatively high accuracy and efficiency, where traditional methods struggled with complex physiological events. Current algorithms often excel at processing digital signals from even multiple different sensors worn together, such as in body area networks, to identify patterns that conventional methods could not handle as well. And so altogether, these advances are helping move wearable technologies from primarily serving as reactive monitors towards providing predictive and personalized healthcare interventions. There are many ways to categorize wearable devices, with one common approach being by form factor and body placement. These categories span the entire body and also many clinical domains. They include accessory and jewelry wearables, such as smart rings, head-mounted or eyewear devices, such as EEG headbands or smart glasses, smart textiles and garments, sensor patches and e-skin devices, such as ECG patches, hearables, and foot-warm platforms as well. However, this list is just an overview and by no means exhaustive. And I'll turn it over to my co-presenter, Dylan, for the next couple slides.
Hi, Arjun. Can you hear me okay?
Yes.
Perfect. Yeah, no, absolutely. And as Arjun mentioned, there's a lot of promise around not only just wearables, but also the work in wearable AI. And I'm a physiotherapist by background, but my PhD was in computer science. So a lot of the research I do is in this umbrella of digital biomarkers. So really just wanted to highlight maybe the direction of travel of where we might be able to harness all of this data. And the reason I'm flagging this is that the traditional definitions of digital biomarkers are very much focused on the traditional sense of wearable technology. So again, it's an exciting area to explore when we consider the more novel approaches of analyzing, as Arjun said, multimodal data and the integration of that. Next slide, please, Arjun. So my clinical work often involves working with people who might have sports-related concussion or other brain health disorders. And one of the challenges that increasingly is apparent when talking about something like digital biomarkers is the understandable nature of the term. So this is a piece of work that I did last year, which was really breaking down a complex topic like digital biomarkers and digital measurements into something which is a little bit more understandable. So this is the walk, talk, think, see, and feel framework, which again, I think highlights firstly the importance of different domains. So we commonly might stratify wearables or different measurements into form factor, as Arjun said, or the analysis, but actually from a patient perspective or a clinician perspective, I think it also makes sense to take a user-centered or patient-centered approach first. So this is a ongoing piece of work. Again, this is disease agnostic, this framework. But again, it's hopefully relating back to the topic or the title of the talk. How does this integrate into clinical workflows? I think is really important. Next slide, please, Arjun. Okay, so yeah, apologies for the resolution on this. I wanted to give an example. It's a very simple example, but this is one which I commonly use. It can be used for other conditions, but Parkinson's disease. So often when we're assessing, or if a clinician was looking at someone who might be at risk or is worried that they might have a neurological disorder, and they might only get these small snapshots. So the advantage if you move to sort of the next part of this, Arjun, is that with things like digital biomarkers, so looking at someone's walking or balance, we get a more holistic picture of someone's gait and balance. And again, that's akin to watching the whole movie, not just the trailer. So a kind of a short analogy just to highlight that there is really a step change that we can gain through simple wearables. But again, when we look at more complex conditions or comorbidities that might be tricky to really understand with one when we just look at one impairment. So I've learned a lot, and really interesting to learn about the work of Ben and others in cardiology. I think with something like brain health, dementia, Parkinson's, we quite often will be looking at a number of different measurements. So again, just pulling it back for the potential value. So that's all I wanted to say. I'll hand you back to Arjun.
Wonderful. Thank you so much, Dylan. Oops. Okay. So, zooming out a bit again and looking at the overall landscape of wearables, for wearable AI systems to achieve reliable performance, devices will need to address several critical technical challenges in data collection and processing. As is the case for many other AI systems, any underlying algorithms utilized must maintain accuracy across different groups of patients, for example, across body habitus, across different ages and comorbidities. As an example, some early wearable AI technologies faced algorithmic bias when models were trained primarily on young, healthy populations, and then faced limitations in generalizability to elderly patients. The original Apple Heart study was one such example where ECG classification performance suffered in a subsequent validation study with older patients. Sensors must also be able to maintain signal quality and filter out noise from constant movement for contact points and varying environmental conditions. For example, modern patches and watches often have the ability to integrate photoplethysmography or microfluidic sweat assay data and may be vulnerable to complications like motion artifact, skin tone differences, and biochemical cross-reactivity, problems that are sometimes more complex than those that plagued earlier generation fitness trackers. Clinical decision support algorithms also demand more computational power than basic step counting does, often requiring complex models to run locally on resource-constrained devices, while ideally maintaining continuous and real-time inference capabilities without frequent charging cycles that could interrupt patient care. And finally, real-time clinical decision support often requires immediate or even sub-second response times for emergency conditions like arrhythmias, for example, which creates challenges around reliable connectivity in healthcare environments and fail-safe mechanisms when connectivity is compromised. There are also several key clinical considerations in the implementation of wearable AI technologies. For widespread adoption to occur, devices supporting diagnostic or therapeutic decision-making will require thorough clinical validation, for instance, through clinical trials demonstrating their efficacy and safety. As described in the last talk, there have certainly been trials in monitors for atrial fibrillation. A recent trial actually in patients with diabetes showed that the use of AI-enabled continuous glucose monitoring in patients was associated with not only better blood sugar control, but also a lower rate of heart failure decompensations, which were in part driven by poor blood sugar control, which incidentally not only demonstrates the device's efficacy for its primary purpose, but also its ability to benefit patients with multiple comorbidities. In addition, Devices require a continuous post-implementation monitoring with systematic tracking of adverse events and regular quality audits to identify emerging safety concerns. Importantly, this overall process ideally involves the critical comparison of the benefits of early detection and potential intervention with the risks of overdiagnosis, unnecessary medical interventions, and turning normal physiological variations into pathological concerns. Successful implementation of wearable AI systems will also require incorporating these devices, which often provide continuous monitoring and a significant amount of generated alerts into existing care workflows without creating alert fatigue or significantly disrupting providers' established clinical routines. Healthcare teams also require comprehensive education on interpreting wearable AI outputs, understanding algorithm limitations and the appropriate clinical context for use, troubleshooting device malfunctions, and also, importantly, effectively communicating AI-derived insights to patients. Legacy electronic health record systems will require modifications and upgrades in many cases to be able to integrate device-generated and continuous data streams, while also ensuring secure data transmission, storage, and interoperability across different platforms and vendors, which has been quite a challenge in practice in the past few years. Devices must also demonstrate some degree of cost effectiveness or return on investment for health systems. And existing remote monitoring and emerging AI reimbursement frameworks must provide a balance to ensure providers are incentivized to utilize these systems, but also not over-incentivized to potentially cause misuse of these tools. The continuous and often intimate nature of data monitoring in wearable devices also creates unique ethical challenges that must be addressed to ensure patient trust and successful adoption of the devices. Healthcare organizations must implement robust security frameworks to protect sensitive health information against data breaches, unauthorized access, and potential misuse by third parties or commercial entities. Patients must fully understand what health data is being collected, how any AI algorithms will analyze and use their personal information, and retain meaningful control over their participation without compromising access to quality care. This can be a particular problem with continuous or 24/7 data collection, and developers and clinicians may need to consider developing opt-in controls and on-device filtering that may allow users to pause recordings or discard unwanted data, potentially mitigating the risk of these always-on wearables, unintentionally intruding on user or even bystander privacy. As an example, recent voice-enabled fitness bands like Amazon's Halo, which was actually recently discontinued, have explored functionality to allow users to explicitly opt into features like tone analysis by creating a voice profile for those consenting, and with their microphones remaining off by default, and then only activating briefly for local processing, and with no data sent to the cloud or to any other entities. As alluded to before, these AI-enabled devices also require rigorous testing and validation across diverse demographics to identify and eliminate algorithmic bias that could exacerbate existing healthcare disparities or provide inferior care to underrepresented populations. And finally, while not always possible, clinical AI systems should ideally seek to provide some documentation or decision traces of how algorithms reached diagnostic or treatment recommendations, or at the very least, provide clinically relevant performance metrics to better enable healthcare providers to trust, verify, and appropriately act on any AI-generated insights. So in summary, this generation of wearable tools certainly has a meaningful potential to improve how we monitor and manage health. But translating that promise into practice means addressing several real-world barriers across systems, people, and technology. And given the sheer scope of these considerations, interdisciplinary collaboration will be critical to allow for their successful implementation in clinical practice. Thank you all for your time.
Thanks so much, Arjun and Dylan. We have a lot of really great questions that have come through the Q&A, and I'd also like to just take a moment to encourage any of the attendees, if you have any questions, please feel free to drop them in to the Q&A, please. We have a lot of great questions. I think the first question that I want to ask is, there have been a few questions regarding just gender differences that may have come up when evaluating and doing research in the wearable space. So I was wondering if you could first maybe speak about, any gender differences.
Arjun, you want to kick off with, and I'll come in after?
Absolutely. So sorry, I think you just cut out there for a second there. Was the question about gender differences in wearable development?
Yes, exactly.
Yeah, no, absolutely. It's a great point, and it's an important point as well. Gender differences certainly can involve physiologic differences, such as variations in body composition, biochemically and hormone cycles, in skin tone even as well. Which can affect sensor performance and data interpretation, which is why it's so important to ensure that diverse demographics are incorporated into the device development process. Historically, many devices, have been developed, tested predominantly in male populations, which has led to potential biases in algorithm performance when applied to different genders. An example that comes to mind, I think, was initial the Fitbit development when they tried to use heart rate monitoring and heart rate variability to identify signs of clinical deterioration. That initial population was predominantly male, and so I think it's going to be increasingly important to ensure that there are standardized, structured ways of evaluating bias, both in device development, but also in device deployment, and thinking about in what populations are we using these devices, and at what points in a patient's clinical care are we using it.
I think we have time for one more question. There's been a lot of curiosity about regulatory agencies and the type of studies that need to happen. I don't expect either of you, Arjun or Dylan, to be an expert on regulatory, but could you maybe speak to the validation process for predictive models?
Yeah, I'll kick off with just I think the broader landscape. I think it's context dependent, clearly on which lens you're looking at it, whether you're looking at it, there's a lot of work from a pharma perspective in digital biomarkers and how they can be used in clinical trials as endpoints. And there's the process associated with that, which are clearly very structured. But I think increasingly there's a recognition that we need to look at what's meaningful to patients. So meaningful aspects of health is really, really important in demonstrating that. So I would say that that's a really, really increasing a critical focus before you even get, and linking back to Arjun's point about, gender differences, I think there's also, it's the age-old debate of form factor and sensor location. But even if you look at something like gait and balance, we often have a huge number of studies with waist-worn devices, and then the clinical translation of those devices is quite challenging. So yeah, there's regulatory challenges and there's broader clinical application challenges. Arjun, I don't know, in 10 seconds or 20 seconds, you want to dip in there?
I think at least from a US perspective, many AI-enabled wearables typically fall under the FDA's software as a medical device framework. And if the device, is substantially equivalent to an already legally marketed device known as a predicate device, it typically follows the 510K pathway. But novel indications without a clear predicate that are, usually low to moderate risk typically follow the de novo process.
Wonderful. Thank you so much. These have been wonderful talks, and I'd like to express my appreciation to all of our speakers, Ben Viggiano, Krishna Pundi, Arjun Mahajan, and Dylan Powell. And thank you to Johanna Kim and the AIMI Center for co-hosting the webinar today. I invite you to the next eWear seminar, which is tomorrow, July 24th. The topic is merging humans and machines, and we have a guest speaker from MIT, Professor Zhuanhe Zhao. A big thank you to all of you, our audience, for taking time to join us, and we hope to see you tomorrow. Take care. Bye.